All right, let's get started. All right. All right, great. It's working today. All right, any general questions before we start? We'll do the quiz in lab after the activity today. More on tomorrow.
Professor Andrew?
Yes.
For the quiz, are you going to provide us with your table you provided us for the class?
No.
But for the exam you will, right?
What? No, I won't. For neither. No.
Oh, okay.
You have to learn how to apply those things by evaluating all parts of the reaction and choose what's best. Yes. The only thing I'll provide for you guys is IR and NMR references values. You don't have to memorize those values. And PKAs maybe, if that's if we need that. Okay. So I'm still grading extra credit, but I did move some of the stuff from the extra credit to your exam scores, so you should see an increase, I think. I'm still correcting majority of the exam corrections though, so I'll try to have those completed by next week. Okay, and then exam 2 corrections, you can start thinking about that. Okay, I got some feedback from me for people that I graded. So when you do these exam corrections, you guys shouldn't type them. Write them all out. Okay, or use your iPad and draw out the structures. Okay, don't just describe the names and stuff. I need to see that you know how to draw it. Okay, so for those people, I've contacted them individually and told them what they should do. It's not like you can't turn in again. You just fix it, and I'll accept it still. Okay. All right, but any general questions? No? All right. So the next homework assignment, alcohols, ethers, a very, very long chapter. Okay? It's 2 chapters in one. All right? So it's also long. So please start on that. Alcohols and ethers will be due not next week, but on the 6th. Okay? All right, guys, let's settle down here. No side conversations. It's a little distracting for some people. All right. So, where did we leave off here? Any questions about anything we went over last time? It's a lot to take in, I know. No? All right. So now we're going to start talking about, let's see. We're going to start talking about oxidation or reaction of alcohol. So not how we make alcohols now. We already gone over that. Now we're going to talk about some reactions alcohols undergo. Okay. So, reactions of alcohols. All right. So like water, alcohols react very dangerously to metals. So have you ever seen sodium been dumped in water? If you dump it in methanol, you'll still hear a large bang. Okay, so it's pretty reactive. So we have formation of alkoxides. So formation of the conjugate bases of alcohols. All right. So for example, you can take 2 of your generic alcohol here plus 2 sodium atoms. Okay, and then what happens here is a single replacement reaction. So the metal is going to switch places with the hydrogen, and what you get here is two formula units of the alkoxide, sodium alkoxide NaOR, and then you get hydrogen gas being produced. So it's explosive because the hydrogen gas produced reacts with oxygen in the air, and then that spark will combust, and will help it combust and make H2. All right, so let's use a generic example here. 2 ethanol molecules plus 2 sodium and you get 2 sodium aldoxide, C2H5 plus H2 gas. And these other ones on the right, don't worry too much about their physical states. Hydrogen gas, we just need to know that's a gas. Okay. All right. So there's other ways to form alkoxides here. We could show the reactivities of alcohols here. Okay. So relative reactivity of deprotonation. So they act as acids. And we went over this. We went over why some of these alcohols are more acidic or less acidic, and that has to do with the bulkiness around the conjugate base. So methanol here, is more acidic than a primary. Like that. Okay. So there's a few other ways that we just don't have to put metal there. All right. We could actually use some other reactions here to deprotonate an alcohol. So I'll give you some examples. All right. An alcohol can be deprotonated quite readily with sodium or potassium hydride, so KH or NaH. Okay. And that will give you the conjugate base of your alcohol, KOR, plus hydrogen gas. You can also use a different strong base, sodium amide. So it has to be like a conjugate, it has to be an atom, a negatively charged atom that is not oxygen. You can't deprotonate an alcohol with a oxygen alkoxide because the equilibrium won't be favored one direction or the other. So you have to use something that's more reactive. So in this case, H, pKa 35, and then I think it's like close to 45. Maybe there's somewhere. But also ammonia, pKa 35. So you have to use something that's higher than oxygen's pKa, which is around 16 for an alcohol. Okay, so ROH plus Na. So we could use also sodium amide as well. That will work. So we get sodium OR, but the byproduct is just a little bit different. We'll get ammonia in this case, and that can just bubble off into your fume hood if we so want it. Okay. So we see here alcohols, they can be readily converted into strong bases. So that what makes them synthetically useful as well. All right, are there any questions about deprotonation of the alcohols? Here.
Oh, I just had a question about
the
physical states, I guess. Because you have the gas.
Oh, yeah, sure.
But what are the other ones?
Usually liquids, solids. And this is probably a solid here. Yeah. You're welcome. Yeah, so all of these are pretty much solids, liquids, liquids. Yeah. So the only time you see liquids here, probably the alcohols. Yeah. Okay, any questions about any other questions about that? Okay. So what's important here that you can actually make your alcohol, and then if you wanted to, you can use this, the alkoxide now, you can use that as a nucleophile in a SN2 reaction, or as a base if you want to use it as to make an alkene. All right, so those are two takeaways there. All right, so relative reactivity there. Now let's talk about a different reaction. So we kind of talked about one already, so let's label this reaction type 1. Now let's talk about oxidation. Okay. All right. Well, we remember oxidation or reduction, right, from Gen Chem, electrochemistry. What was the definition of oxidation? You losing electrons, right? And then reduction, gain electrons. Okay, good. In OChem, we don't care about those terms. We use different terms. Okay, so oxidation is a little bit different. So oxidation, we're going to say, is increase the number of bonds to oxygen. Or in the case of there's no oxygen, you just think more double bonds or less bonds to hydrogen, okay? Increase the number of bonds to hydrogen, or less bonds to hydrogen. Okay, so we don't do this counting. You can count, but it's not really necessary. Okay, so for example, we'll go over some examples. Okay, with the alcohol example, we'll see that there's a decrease in the number of bonds to oxygen, and that indicates a reduction. And if you increase the number of bonds to oxygen, like for example, aldehyde to carboxylic acid, you're increasing the number of bonds to oxygen. That is oxidation. All right, so reduction here, maybe I just spell it out for us. Reduction is you have you're decreasing the number of bonds to oxygen, okay, or more bonds to hydrogen. Okay, that's the difference there. The more bonds you have to hydrogen, the more reduced you are. So the highest oxidation state, so there's a few here. There's a list of oxidation states, okay? So I'm just going to give you the most reduced and the most oxidized. And the other functional groups, they come in between, but you could kind of see like why one's most reduced and why one is most oxidized based on the number of bonds they have. All right, so in organic here, methane is the most reduced. And I think we can see why, right? Because how many oxygen atoms are in here? None, right? So that's the most reduced form. There's a problem because what happens to methane? It just sits in landfill and it becomes a natural phenomenon, right? So got to something about methane, all right? Can't break it down. And then over here, the most, so there's going to be some functional groups in between here. But in terms of chemistry of organic, usually carboxylic acids are the most oxidized. Because the only way you can oxidize that more is to go to CO2. And you can do that. with carboxylic acid, but it won't be considered an organic compound no more. And CO2, there's not much use for CO2 in terms of what transformations you can get because it's so simple. So this is most oxidized. Okay. So here I wanna demonstrate something. Let's see. Well, I'll do it a little bit later. Okay. So yeah, because the word oxidation kind of sounds like oxygen. So if you add more oxygen, oxidize. If you remove oxygen and replace that with hydrogen, that's considered more reduced. Okay. We don't consider replacing it with carbon atoms because that's usually trickier to do. So it's more in terms of hydrogen and oxygen. Okay, are any questions on those terminology? So we'll have to be able to recognize when something's reduced and oxidized. So you have to compare before and after how many oxygens there are, or how many bonds to oxygens there are, versus how many bonds to hydrogen there are. Okay, so let's do some examples. Like what reactions will this fall under? Okay, so let's put a line through there. All right, so we talked about oxidation and alcohol. So here's the second reaction. All right, so oxidation. We have to remember a few reagents here. So most commonly used reagent. Well, despite this reagent being so old and now kind of notorious because it's a carcinogen, it's chromium-6. Okay, so that's the metal. So when you have a metal in high oxidation state, it likes to act as an oxidizing agent because it wants to gain electrons. It's too high of an oxidation state. Okay, so what commonly happens here is that chromium-6, so Cr6+, they will react with a bunch of organic compounds and undergo reduction. And when they undergo reduction, you get a different chromium species here. So one is orange and one is green. So you can actually tell when something has oxidized is because this reaction has taken place. Chromium-6 has been reduced to chromium-3. Okay? So that's a common way to determine if something has an alcohol. You would test your alcohol using a chromium reagent. If it turns colors, it has a presence of an alcohol. And these reagents usually only react with alcohols. Whereas other oxidizing agents, they can react with double bonds, alkenes, and they can cleave them. So this one is very selective. So that's why it's so useful, despite its dangers. Okay, so the most common ones we'll see is PCC. So chromium-6 and PCC. So PCC is a mixture of chromium trioxide, or chromium-3 oxide, chromium-6 oxide, HCl, and pyridine.
What's it, Andrew?
Yeah, what's up?
Sorry, the numbers are throwing us off. Did you mean like 3 instead of 2?
No. What do you mean?
Where you have next to most commonly used oxidizing to the.
Oh yeah, sorry. I guess that should be. No, it should be. It's still part of this one, number 2. Let's just erase that.
Okay, that's
Sorry about that. All right, so we had a mixture of chromium trioxide, HCl, and then pyridine here. So pyridine is benzene, but there's a nitrogen inside the ring. All right, so let me make that a little more clear. Nitrogen in the ring, right there. All right, so that's pyridine. It's commonly used as a weak base in organic. So it's commonly used where you need a weak base to complete the transformation. So that's what we have here. All right, so these will combine. You don't need to know how this forms. Don't worry about it. This is now forms an ion. Called pyridinium chlorochromate. All right, so the HCl will protonate the pyridine, and then part of one of the oxygens will be attacked by this chloride, and you get pyridinium chlorochromate. That's PCC. No, it's called chromate because it's a negative charged oxygen anion. Okay, so that's PCC. Now, you don't have to draw PCC every time you come across it or you need to use it in a reaction. You can just write PCC. Okay, I know what you'll mean. So that's PCC, pyridinium chlorochromate. So just remember that acronym, and that it's an oxidizing agent. Okay, use it to convert alcohols to ketones or aldehydes. All right. Now the classic reagent we use historically in the labs as well is called Jones reagent. All right, and this is probably named after the chemist who discovered this reagent. All right. So it uses the toxic chromate salts to form chromic acid. So sodium dichromate or sodium chromate, CrO4, plus water, plus H2SO4. So for these chromate salts, you can also use potassium. Sodium or potassium would work, all right? It doesn't just have to be sodium. All right, and so when you have water in there, you create a very powerful oxidizing agent, and that's called chromic acid. So this will form chromic acid, all right? So in abbreviation, what this creates is H2CO4, CrO4, chromic acid, all right? So chromic acid is a powerful oxidizing agent, and you kind of see here, it looks very similar to PCC, except you have one less oxygen atom, okay? So this one's more reactive than PCC. All right, so let's show you some examples where we will put this reagent into action here. So we have all right. So what kind of alcohol is this? Like if you had to classify the type of alcohol, 1, 2, or 3? Boop, 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 boop. All right, so this is a secondary alcohol. So let's put a secondary right here. So we have a secondary alcohol. All right, what happens here is the H and the H from the oxygen, they will be cleaved off, and you will get a ketone. All right, and you see this example right here. We can see right here that this carbon now has how many, on the right, has how many bonds to oxygen now compared to the left? 2. So again, one more bond to oxygen, that's oxidation. Okay? We already talked about the reverse process, ketone going to alcohol. You have one additional H bond now and one less oxygen bond. That's called reduction. Okay? So in this direction, we have oxidation, okay? And in this direction, if we had, for example, sodium borohydride and an alcohol, that will be called reduction. So you can go both ways using different conditions, okay? Whether or not they both work the same way in terms of do you get 100% yield or not, that's another story. Okay, but that's two ways you can go from one reactant to the other, and the other way by oxidation and reduction processes. Okay, are any questions about that one? We'll go over the mechanism, but not just yet. Okay. All right. So, well, we have another scenario. So, oxidation here, you need two things. So let me just highlight that right now. You need this and this H. Okay? So oxidation, you are minusing two H atoms. But reduction, what are we doing? If we're oxidizing, we're removing two hydrogen atoms from the molecule, what do you think reduction is doing? Yeah, you're adding, right? You're going to add two H's, right? Notice here I didn't put a plus or minus charge with H because I'm just telling you, you're just adding two hydrogen atoms across the carbon-oxygen bond. All right. So now let's look at primary. All right, so you will get two different reactivities here based on what reagent you use. All right, if you use PCC, this PCC is called a mild oxidant. It's very selective to get you aldehydes. Jones reagent is considered a harsh oxidant. It is very reactive. If you have any acid-sensitive functional groups, it will destroy them. Okay, it will pretty much remove them from your molecule, and that brings up Pandora's box of issues for a chemist. Okay, so PCC here, you stop at the aldehyde. And the really difference here, why that happens, is because one of these reagents, one of these reagents has water. Which one has water? Is it PCC or Jones? Jones, you need water. You need water there to form that additional oxygen on. See this additional oxygen right here on the chromic acid. Usually, water is needed to do that. These chromates. Well, I'll tell you what water is used for in a bit, but it helps the over-oxidation. Okay, so just imagine your aldehyde right here. If there's water present anywhere, the water will attack it, and then it can further oxidize. I'll show you what I mean in a bit. All right, so then primary with Jones. All right. What do you think this one can go to? What would be the over-oxidized product of an aldehyde? Any ideas? So what's the other functional group that looks like an aldehyde but has an extra oxygen? It's probably going to be, all right, it's an acid. A carboxylic acid right here. Okay? So that's why aldehydes or dienes will just OH groups and aldehydes like milk. Okay? They don't last long in air because if you don't get it home fast enough and in the fridge, it's going to slowly convert to carboxylic acids and it'll get all gross, chunky, smells sour. All right, so you gotta be careful. And that's because aldehydes, they're very sensitive to oxidation. And if there's water moisture anywhere, where it is milk, probably so, you're going to get a carboxylic acid. Okay, so I'll show you what happens here. Why we get a carboxylic acid when we use Jones reagent. Okay, so here I want to show you over oxidation of aldehydes. Two carboxylic acids. All right. So we know R, OH. So the first thing that happens is, say you have sodium. All right, did I put sodium 2? Yeah, I did. Sodium 2, CrO7, sorry, Cr2O7, H2SO4. So this is just a strong acid, and then H2O. All right, so first thing you'll get is an aldehyde. All right, there's no question about that, because PCC did that, so this will do that too. However, there's water present right here. And what water likes to do, it will attack the carbonyl, and you'll get a hydrate. Okay, so this is what happens. So you get a hydrate, OH, OH, and here's the H. Oh, look what we have. We have an H and an H. One more H now, another H here. So if I use Jones reagent again, okay, well, sorry, rewrite that. All right, more Jones reagent, Na2, Cr2O7, H2SO4, H2O. Now, that hydrogen will be lost, and what you get is a double bond O and the OH that was not touched, carboxylic acid. Now, the reason why PCC works as well as it did is because there's no water, all right? So when there's no water, in the absence of water, okay, no further oxidation takes place. All right, so you won't get the conversion from aldehyde to carboxylic acid in that case. So that's why we choose PCC. Now, they both contain hypervalent chromium, so chromium in a high oxidation state or charge. So they're still not good. They're safer reagents we use nowadays. The only downside now is they produce very smelly byproducts. So I don't know. I guess we'll take that over cancer-causing compounds. Okay? All right, any questions about oxidation of these alcohols? All right. Next, we'll go over how this process takes place mechanistically, so step by step. Okay. All right. So I'll show you a few things first. How do we form PCC? Okay. I'm going to show you the whole mechanism for this oxidation here. All right. So chromium trioxide. All right. Remember we wrote HCl? So HCl is in equilibrium with the formation of this PCC reagent. So we get H here, chromium leaves, chlorine is going to depart. All right, so Cl minus will attack the chromium because chromium's a metal, so it's electropositive in some sense. Okay, bam, it'll now form what looks like the pyridinium chromate. So CrO. Cl. And then here we have OH. All right. So, oops, I didn't mean to do that. Erase that. Okay. So, the reason why this hydrogen is particularly acidic is because it's right next to the chromium and it can do resonance once we show how it loses its hydrogen. So, let's draw a pyridine. All right. Let's see if I draw it correctly. Nope, I already messed up. All right. So, boom. My bad, guys. Let's do it this way. Like that. Okay. Takes that H, goes back to this O, and then what we're left with is PCC. So that's how PCC would form. All right, if we're curious how that works that way. All right, so this is PCC, pyridinium, chromate, like we saw before. All right, so the question is, how does this react to get your alcohol? Okay, so you're going to have your alcohol here. So this generically, let's just have our two R's here. Let's make them two different alkyl groups, OH, and here's H. So my secondary alcohol. All right, let's draw pyridinium. So this is going to do something like an SN2 reaction here. But we're not worried about the stereochemistry. Don't worry about that. Okay, then Cl minus gets ejected. And now we have our alcohol bonded to this chromate ester. Okay, so now this oxygen has a positive charge. Okay, so here I'm just going to write let's see, what should I put? All right, here is what we call PT. This stands for H plus transfer. All right, so we do that. We're transferring the hydrogen to the other side, okay? So our group here. So the only reason we would say this is because we don't have a good mechanism or understanding of where exactly or how exactly the hydrogen gets there. So sometimes we just say proton transfer, okay? So boom, O, chromium, oxygen, OH. So you see here the hydrogen has switched places there. And we do that for a reason. Okay, so now let's draw our pyridine molecule. All right. So this is the reason we need the base and we need a hydrogen. All right, so this is what we call a chromate ester. So chromate ester. All right, because it has a double bond O, and it's connected to a singly bonded oxygen that's connected to a carbon group. So that's why it's a chromic ester. Now, so this is going to be like an E2-like reaction, okay? But don't worry, you don't need to know what exactly this mechanism is, okay? So now this electron is going to go back there. So now what happens here is your R group and the alcohol has been converted to a ketone. That's what that double bond is telling you. Plus HCr O3. Okay. And then plus pyridine, which we can write as H bonded to N. Sorry, I did my best there. Okay. So chromium CR7, 6, has gone to chromium 3. Okay, and the reason why it's gone to chromium 3 is because now we have actually removed one of the double bonds. So that's why it's now chromium 3. So yellow, orange. And like we said before, and this is pretty much dark green. So if you have an alcohol, you dump PCC in there, and it's in solution, and there's an initial color change. So PCC will look orange, yellow-orange. And then your solution, if it turns dark green, that means you had an alcohol in there, either primary or secondary. Okay, so that's our first look at a long mechanism there. Are any questions?
Yeah, can you repeat what you said about the alcohol?
What part?
The last part, the color change?
Yeah, so you have an alcohol and you add PCC in there and your solution turns green, dark green. That means an alcohol is present. Yeah, say you have an unknown mixture of, you don't know what your mixture contains. If you take some PCC or Jones reagent, dump it into your solution, and if there's an immediate change to dark green, that means you have an alcohol. All right. Any other questions? Yes, Alondra. No, so if you can just, you just remember, alcohol goes to ketone or Jones primary to carboxylic acid. That's all you really have to know. Yeah, I won't ask you to reproduce this, but for those of you curious, this is how it works. Yeah. Jones? Oh, PCC. This PCC, it just turns into this. Pyridine, pyridinium, and then that's a form of chromic acid. I think it's like the conjugate base, I believe. Oh, no, it's neutralized now, so yeah. Oh, sorry, I forgot the charge. Let's put plus charge right here. Okay. There you go. Okay. All right. So now let's talk about what happens when we put acids without alcohols. Okay. So this is our third class of reactions. Alcohols plus strong acids gives you ethers. Okay. All right, but first let's talk about something. What did we say about? So what are the bad leaving groups from chapter 11? There's two of them we talked about. Well, we know carbon groups and hydrogen, they can't leave. But what also are bad leaving groups? There's one halogen. You guys remember which halogen is a bad leaving group? Fluorine. And then what other? Well, we use an alcohol, right? To form we use OH minus to form an alcohol from an SN2 reaction. Could we then use that in an SN2 reaction? No. Hydroxide is very bad. Okay? So that's why we need acids to convert alcohols to a very good leaving group. Well, I wouldn't say very good. A decent leaving group, and that's water. Okay? So we're going to convert OH to a good leaving group. Okay? So, what strong acids do this? So let's talk about that. Strong acids. So, nucleophilic acids. So you have two classes here, nucleophilic acids. So they are acids with conjugate bases. So acids with conjugate bases that are nucleophiles. Okay, so they are HCl, HBr, HI, and sometimes some form of RCO2H. So what I mean by that, so some carboxylic acids, they can be turned quite strong, all right, and they can do this, but they're rare, and we probably won't talk about much examples, but this also falls under that class, okay? All right, then you have something called non-nucleophilic. H2SO4. So these are acids whose conjugate base are rendered unnucleophilic or non-nucleophilic because of resonance. HF. And HF is just so weak that it won't react at all. Fluoride is too weak, so it won't want to give up its electron. So we usually never see this in this type of reaction. HF won't work because of fluorine's too high electronegativity there. All right. So you can use this process to give you primary alkyl halides. So we could do the first one, reactions of primary alcohols with HX. X equals Br or I. Chlorine can work, but it's very slow. You need something called Lucas's reagent to help to get it go. So I would say here, let's put a comma here, with Cl, a catalyst is needed. So catalyst needed. In this case, you'll need a Lewis acid catalyst. So zinc chloride is a common one that they use. Anhydrous zinc chloride, or zinc chloride that has no water in it. All right. So solids, they come in two forms, anhydrous or as a hydrate. Typically anhydrous works best, especially for organic ones. Stuff are so water sensitive. Okay, so let's give an example. So R, CH2, so this is our primary, OH, plus HX, going to RCH2X plus H2O. Okay, so that's our generic example. Let's do the example RCH2OH plus HBr. So HBr would work pretty well. It's a very strong acid, so CH2Br plus water. All right. Well, we see the reaction here. Probably questions of how water forms. So we'll go over the mechanism next. All right. So are there any questions before I move on? I'll just move it up a little bit over here. All right, here's the mechanism. R, CH2. So just remember the mechanisms. You see all these steps, right? But don't think, oh, I have to memorize all these steps. Think about what's the likely thing to happen when you have something with lone pairs and something that's acidic. An acid-base step, right? So that should be our first thought. Acid-base chemistry here. So HBr. So what do you guys think is going to happen first? Any ideas? Yes. So protonation but a strong acid. Very good. Now we have R, CH2. Now look at here. This oxygen now has a positive charge. So what's better? If the leaving group is neutral or if the leaving group has a negative charge and it's on oxygen? No. Actually, don't worry. Just think of it this way, right? Neutral, more stable than a negative charge. But the electrons are still going to oxygen, so they're still favorable either way. But it's just it's more stable if water leaves, because water is a very weak base, whereas hydroxide will pick up any free-flowing H plus ion it sees, right? So let's just think of this way. Well, we probably can't. It won't probably happen through SN1 because we can't have primary carbocations, or they're just too energetically unaccessible. So we're going to do it by an SN2 type SN2 mechanism. So the second step is displacement of the good leaving group, water, to form the primary alkyl halide, Br, plus H2O as your byproduct. And then separation of this product is quite simple. You can simply just distill off the water. Or, no, I think you would distill off the bromide, and that will come off pretty easily before the water ever does. All right. Any question about this mechanism? Well, let's think we have. Our nucleophile is good. Primary substrate, SN2. All right, but any other questions before we move on? No? All right. Reaction. So that was primary. Let's now do secondary and tertiary. So reactions of secondary alcohols with HX. All right, so this will work with Cl, Br, and I. And that's because most of the time in these type of reactions, secondary and tertiary, they'll go through SN1. And that's because forming a carbocation is relatively easier in these cases. So that's why we go through an SN1 mechanism. All right, so the example I would use is this one, isopropanol Okay. All right. Well, secondary, not substrate is a little more bulky, so the alcohol likes to get protonated first, leave to form a carbocation, and then the nucleophile attacks the carbocation, and you get to the product. But let me show you how that works. So let's do the mechanism. Well, what happens first in the mechanism, just like the previous one, what was the first step we did? All right, which of where?
Of the hydrochloric acid.
Yes, thank you. Good, so Cl minus gets liberated here. And then you get OH2. This is a better leaving group than hydroxide, so that's why it leaves, okay, through this SN1 process. H2O. All right. All right, so what's the last step we have to do to get to the alkyl chloride there? All right, what's the Cl going to do?
It's gonna grab it.
Hmm?
It's gonna grab another hydrogen.
No.
It's gonna jump.
It's going to be attracted to the positive charge, right? And we're going to form a bond there. And we get the alkyl chloride right here, SN1. So this is an SN1 mechanism right there. Now, if this is kept relatively cold, so 0 degrees or this might just proceed through give you this product. But if you raise the temperature, if you start raising it to like hot temperatures, it might give you some E1 product, okay? All right, so there's no temperature specified. You're always safe to say that your product should be both SN1/E1, okay? So make sure you draw both if that's the scenario you have. All right. Okay. Well, let's take a break here because the next part is going to be a doozy. Okay. Carbocation rearrangement. So let's take a break right now. Okay. Any questions?
Yeah, I'm just to clarify, you said that there isn't heat specified, but to draw both.
Yeah. So if I don't specify it's cold or hot, you should draw both SN1 and E1.
Is that just for alcoholic or in general?
In general, when you have an SN1 E1 mechanism. Yeah. What's up, Marita? What? Oh, jokes. What time? Just let me know. I can have you take it outside. An hour. Yeah, around 5 minutes, right? Definitely. Yeah.
What's going? I
didn't see you guys today. Wow.
my physics lab ran until 11:30 from this morning, and typically I'm able to get out early, but she wanted us to stay until the end to do the like when you write your review on the professor.
Okay.
Yeah, she made. Yeah.
What do you mean? Like someone came in?
Yeah.
Yeah, she's being evaluated, right?
Yeah, evaluation. She's like, you have to stay, and I'm like,
Oh, you're forced to. Yeah, you have to.
Yeah, but I'm gonna do Monday.
Okay. Jacqueline, what are you? Okay, got it. Sweet. You're keeping track of that, right?
Yeah.
Good. Chapter 11. Yeah.
I mean,
Lucy, how are you doing? Okay. Sure. You should do 2 minutes there too. Go to Marshall, spend at least like 40%. No, that's just what it is. But you go to our office hours too, don't you? Yeah, do you? Oh.
It's really busy today.
I see. Yeah, okay.
more than
We'll
that.
go to our website now, just let me know.
For office hours?
No, I can
Oh, I guess I is.
Well, you saw your score, right? You did good.
To her office hours.
You did very well.
So it's more extra credit. Oh, got it. No, yeah, I did that's what I did last time. I did 2 and then did you read it? Yeah, I was gonna do that. Good to see you.
It's you. I know.
He doesn't know if I'm like that.
Are you gonna take a thing with others?
Well, you missed the other one. You missed
Why
last
did you
time.
come to your office hours?
Well, you only have a week
For what?
to make it up. It's almost, it's in a week.
What do you mean I have a week?
That's the policy. That's in the syllabus. You have a week to make it up. There you go. So you don't forget about it. Yeah.
So I need to make it.
No. Today, if you can.
Today?
Yeah.
Why?
We're, yeah, today, so I can hand back the quizzes.
You can handle that even if I double the answer, I'm still not here.
No. I trust you guys, but not that much.
Even if you have me to help you with that. I should go get it wrong. Oh, today? What if I come tomorrow? What's today?
No, I'm busy tomorrow. I can't make that. I teach other places too.
Yeah. Well, I'll go when you're.
Where do you teach?
SCC.
Really?
Sac City?
The same class?
No, I teach a research class.
Oh, okay.
We're working on isolating compounds from cannabis.
Oh, wow.
Is it on mail? I sent this question You have to send a different question. The little Just send it to her though. I don't want the professor to make sure you mail it again. I'll send it to her. I'll take my makeup.
See, you're dedicated. You have a whole one. That's wonderful.
Like that on us.
She wants to get on the good side. You're gonna get ready to
I'm gonna put it right there. No, because then we'll see it.
So he has this little doll. He doesn't have to do, but I seen it. Where is she? Oh. Here she is. So this is a little doll, and I guess they put a little like the stick on her, cause she's nice. So she's nice when she has the stick, but when the stick comes out, it turns into the little evil doll like. So I've been telling him, be nice to us, because you're so mean on the test. So he's a little, no, you're like, it's not home.
Yeah, he deserves to know. It's yours. You gave it to him.
You gave that to him? What? No, so he has a little.
What's this?
What?
What is this for? Thanks.
What is it?
The Funko Pop. No. Hi, what's up?
I actually won't be able to stay for the lab.
Okay.
I have to go pick up my baby. For
Okay.
the quiz, can I just replace it or can I retake
You could take it next week if you want. Come during office hours.
on Tuesday if I can.
Yeah, Tuesday or Thursday, whatever works best.
Okay, that's fine.
She's like, what's wrong with you?
I'm also eating in my lunch this morning. Breakfast. Because I grew up in North, like eating my breakfast. Depends on what I eat.
Yeah, I did. Thank you so much.
I'll like put it on my laptop.
Oh, no, I don't have my iPad. I'll like connect it.
But I don't know the way.
Unless I really
Maybe I'm thinking about
Or like sometimes I don't like to roll
Oh, that's good.
Or like if you use it.
All right, well, let's just pick up where we left off. All right, so there's a problem with carbocations. We didn't really touch upon this last chapter, but they tend to rearrange, okay? So sometimes the charge likes to dance around the molecule and just go to different locations. That's the best way I could put it. All right. So, limitations to carbocations. Carbocation rearrangement. So whenever you see carbocations forming, you should ask yourself, okay, is this carbocation nearby a carbon that is more substituted? If the answer is yes, then it's possible you can do a rearrangement, okay? So, for example, if we take this alcohol, and in the homework, you might have seen a question be like, okay, draw the expected product, assume no carbocation rearrangements. Now we have to consider that, okay? So we take HBr, 0 degrees Celsius. You get a product distribution that is not what you expect. All right, so how the hell did the bromine get on that position? Okay, and then where did the hydrogen go from that carbon? So you expect this product, but in fact, this is the minor product. How does that happen? Okay. So let's go into the mechanism of this rearrangement, okay? So the mechanism of carbocation rearrangement. All right, HBr. So the same few steps we've seen before. We will protonate first. Then bromine will come around here and attack the carbocation. But what tends to happen first is that these rearrangements are so fast that it'll rearrange before bromine can even approach it. Okay? So these are really fast reactions. So the first step here is a carbocation formation. So what happens here is that this hydrogen atom here, its orbital is so nearby, okay, so it's so close by here, that this p orbital that's like right over here, so the p orbital here, oops, I didn't mean to do that, okay. It can actually just interact here with the positive charge, okay. So what happens here is that this hydrogen bond is going to go to this carbon, okay? And we call this a 1,2 hydride shift because both electrons are moving. So I could redraw this just to make sure this is a little bit more clear, okay? So it's like the hydrogen atom is moving one carbon across, like that. And the result of that is you get an isomer of the carbocation. This is a plus charge now. Okay? Now the bromine, since it's a much more stable carbocation, secondary versus tertiary, this one will be stable enough to exist, and that bromine can come by and form the product. All right. All right, so here I'll leave a little note. As long as the carbocation can form, the precursor does not matter. Does anyone have any questions about like what I mean by precursor? I mean that it doesn't matter if it came from an alcohol as a leaving group, an alkyl halide, or any carbon atom with a good leaving group, an sp3 type leaving group. Okay, as long as you don't have that, the carbocation will form. Doesn't matter what the leaving group is, as long as it's a sufficiently good leaving group, it can form. Okay. All right. Are there any questions about that? No? All right, we're going to do some more examples of carbocations rearranging, okay? So you get an idea that this is just not restricted to these simple compounds. It actually happens a lot. All right. So let's get a new page here. I'll add a board. All right, so let's do some more examples. So let's talk about how do we know that carbocations can exist? Well, if we record NMR spectrums, so remember we're talking about NMR right now. So we take an NMR spectrum of a carbocation at very low temperatures. It's stable enough to exist, and we can capture that image of the carbocation on the NMR timescale and actually get its chemical shift. Okay? And the chemical shift is quite large. Very deshielded because of the carbocation's ability to attract electrons. So let's say we have this tosylate group. And then this is an acid, okay? So this is a very strong acid. And what it does, it promotes the leaving group to leave, but then it stabilizes the carbocation by interacting with it. But it doesn't actually form a bond, okay, in solution. So at negative 77 degrees Celsius, so to get to this temperature, you would need to use dry ice in acetone, a bath. Okay, a very cold bath. And then this would form and you can observe it. So here You can observe through NMR. Okay. So this also goes through a rearrangement mechanism. As you can see here, how does that carbocation form if we think a primary carbocation is leaving? So what happens here is you have a concerted methyl shift, and the leaving group leaves, like in an internal SN2 reaction. So what happens here is this methyl group is going to form a new bond here, so it's going to dance over or slide over, and the tosylate group gets kicked out. And so you get this carbocation forming. Like that one. So this is called a 1,2 methyl shift. And that's because the methyl group is the one moving its electrons to the nearby carbon instead of a hydrogen. Okay. All right, so carbocations, they can form. We'll actually see a situation where a primary cation looks like it's forming, and that's just a. So that's why we can't just say, oh, primary carbocations, they never form. They do under extreme conditions. Okay, and the person who did this stuff, he won a Nobel Prize just for doing this. All right, for our understanding of these carbocations. Okay, so let me show you a different example. But are any questions on this one? Okay, so what I want to get across is you just don't want to memorize, it seems like, these like reactions, because sometimes I want to ask you, okay, here's this reaction. It's expected to do this, but it doesn't do that. Explain with a mechanism. Okay, so we need to be proficient here, good drawing these arrows. Okay, that's an important skill to have, and it'll help make getting through this class a lot easier. Okay, all right, but any questions so far? No? All right, so let's do another example. Here's example number 2. All right, so if we take this secondary alkyl halide, and then we add antimony, SBF5, and this group here, this very exotic looking chemical right here, and at -7 degrees Celsius, you can actually get the chloride to leave, and you can observe the secondary carbocation. But immediately after you warm it up a bit, it will immediately rearrange to the tertiary carbocation, so it'll rearrange to this one. So it's kind of weird what these things do under these conditions, all right? So you think, oh, it's really cold, it shouldn't just be stable. But no, if you have in the presence of some, we call these coordinating anions, so they stabilize the carbocations. So don't worry too much about what these reagents do. They just help the carbocation form, okay? So how does this work? Well, we can think of it like this. Here's the carbocation, so minus Cl, minus here. All right. Boop, 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 boop. All right. I drew it the other way in my drawings here. So let's just put it here. It's symmetrical, so it doesn't matter where you draw it. As long as it's on the second carbon atom, it'll go like that. All right, so let's number our carbons here to just indicate how the movements in the rearrangement are occurring. All right, so this group here, we're going to move it to the carbocation. And what we get here is an isopropyl group. So here's my methyl group, okay? So let me just put the methyl notation here to indicate that one is the one that moved, okay? And then if we number the carbons again, 1, 2, 3, and here's my fourth one, okay? Now, where's the positive charge going to be? Well, we just broke the bond to carbon-3, so that no longer has an octet, so a positive charge will go over there. And then, how do we get to this final structure right here? Well, we're going to do a hydride shift. So this is going to go attached to this carbon, and now we get to this group right here, okay? And then we can also draw this as, if we're numbered, let's draw it the way we numbered our carbons. So H right here, methyl right here, and then our carbons, we numbered them 1, 2, 3, and then 4. So I find it that when you're starting drawing mechanisms, just numbering the carbons, they will help a lot, especially when you have these rearrangements. They'll look tricky to do, okay? All right. Are any questions about that one? Just here in my product there, or my carbocation right there. So I didn't draw the positive charge. Let's put it back. So the positive charge just moved around. It looked like it just changed places. All right. Any other questions on that one? All right, now we're going to do a little more advanced one, okay? So this happens in more advanced structures where it seems like a bond is appearing and then disappearing, okay? All right. All right. So you can also have structures like this. All right, just bear with me here. So this is a bridgehead. All right, so let's try drawing that. It looks like a propeller. All right. So in this structure, there's actually 2 rings connected in this structure. If you look at the left side and go to the apex of that, we call that a bridgehead. It's connecting the two. It's like a bridge, okay? And then the other side, there's another ring, if you kind of count the carbons there. So what I want to imply here is that that bond to the front here, this bond right here, this bond is going over this bond. It's not actually connected to that bond it intersects. So maybe let me modify this drawing a little bit, okay? Just to get that point across. So it looks like this. And the bond, see the bond has kind of going in front of the bond and back. So they're not connected, okay? So I'm going to number the carbons here to make that easier to see. All right, 1, 2, 3, 5, 6, 7. And then there's a methyl group here. So this is number 8 right there. Okay.
Methyl group off the top where you have the 1.
No, so that 1 is where they join.
Okay.
Yeah, I'm not going to number the methyl groups just for simplicity there. All right, so the 1 is actually pointing to the central carbon at the top of that peak, where the methyl groups are kind of fanning out from. So that's number 1. So number 1, let's just put an arrow here. It's pointing to this carbon right there. Well, yeah, I don't know if you guys can see that. So carbon number 1 is this carbon right there. Okay, so there's an alcohol here. All right, H plus. All right, so this is a structure. All right, I have to draw it up front. All right, so this is a structure called camphene. So we will work with this compound, but it's called camphor. And we'll turn it into isoborneol. So camphor has a very medicinal-like scent, very minty, very, very strong. But it's in vapor rub, Vicks vapor rub, and some cough drops. Okay, so that's caffeine. So we're going to see how does this structure form, okay? Because it looks like it's been rotated or something. So we're going to figure out how this one rearranges, okay? All right, so let's go over the mechanism. Now this is purely just for illustrative purposes, okay? I'm just showing you how these rearrangements, they can get a little complicated here. All right, so here's the mechanism. Our water gets protonated. Okay, let's see. I want to draw this. Boom, boom. All right. H2O plus. All right, let's number again. 1, 2, 3, 4, 5, 6, 7. And then there's methyl group coming out. That's letter 8. All right. So the water is going to leave. And then we're going to get our carbocation on the carbon number 6. Okay? So carbon number 6. All right. Well, this is actually going to rearrange, so we get a tertiary carbocation. So let's renumber this too. 1, 2, 3, 4, 5, 6, 7. All right, so there's going to be a rearrangement here. So we're going to break carbon 4 and 5. So I'm going to write here C4, C5 breaks. All right, so this carbon, let me just circle it so it's kind of easier to see here. And let's mark that in red. So this is going to form a bond to carbon number 6. Okay, so we're going to have a C4 to C6 bond forms. All right, now it's going to look something like this. Okay, so let's just draw. Okay, boom, boom. Okay, well, all right, let's raise that a little bit. Okay. All right, so this is gonna look a little weird. 6, 4, 3. This is what's going to the bridgehead, so that's number 5. Then boom, boom. Number 1. Number 2, and here's 7, okay? And the positive charge now, this is 8. 8's coming out across here over this bond, so that's not actually a bond there. So now this carbon in the center where 5 is has a positive charge. All right, so now it's going to look kind of strange. How do we get from this to that up there? Do we have to make more disconnections? The answer is no. We just have to rotate this a bit. So we're going to now begin to rotate this around sequentially by 90 degrees. So let's rotate this 90 degrees. All right. Whoops, I didn't mean to draw like that, but oh well. So it's all about perspective here. So it looks like this looks like it looks very confusing, but it's actually not. Okay, so here, boom, 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 boom. All right, 1, 2, 6, 3, 4, and this guy is 7. Okay, so we kind of. So if you think about, see each 7 here? So each of these points here, they look like they can just be this group up here, right? So that's what this point is. This point turned into this point because I rotate it around 90 degrees. I know it's very hard to kind of visualize that on paper. But just imagine you're rotating a bit and then all the pieces are sticking out based on how you rotate it. Okay, so let's rotate it one more time. Rotate that 90 degrees. Okay, now we get, this looks very similar to what we have before, is now flipped on its side. One position right there. And then we have the 2 position right there. 7, 3, 4, 6. And then here's number 8. And here's 5. And this is just a hydrogen bond I'm showing for simplicity. And then the carbocation is still at position 5. So we get now our base, water, which has left. It's now going to deprotonate that and give you this structure right here. And there we have it. That's campheine. All right. So it rearranges, and then you form. It looks like an isomer, right? It looks like the bridgehead and double bond, or the 2 methyl groups here, kind of just switch places. If you think about it, like this one and this one. But in reality, what's happening is you form a different bond. And then you rotate, get to this side of the structure. And so then you can see how the bonds kind of appear now in the product. All right, don't worry, you don't have to reproduce that on exam rating. Okay, don't worry about that. I'm just showing you how carbocation rearrangements, they explain a lot. Yes?
Can you go back up? I didn't get for the iso, what is that?
Oh, isoborneol. Yeah. We'll be making that. So isoborneol. So this compound without the OH is called isobornene, and it's a classical example of carbocation rearrangements in the history of chemistry here. It's a weird one. All right. We'll just go over 2 more examples, okay? And then that'll be it for carbocation rearrangements. And then we'll talk about alkene synthesis from alcohols next time. All right. So that's campheine. So there's 2 more. All right. Now I want to show you when the ring can mysteriously change sizes midway through the reaction. Okay, that's called ring contraction / expansion. All right, and it happens too. So I'm gonna now again we're working with the bridge heads. So just bear with me here. Boom, boom, boom. All right. One, 2, 3, 4. Oh, sorry, there's a methyl group here. 5 and 6. All right. So when this is all said and done, somehow you get this.
Mr. Andrew,
Yeah, what's up?
the previous method that we just did, with,
Yeah.
like the numbering, is that going to be on active?
No. All right, so somehow you get this. 5, 6, 4, 3, 2. All right, just leave that carbon unnumbered because I left it unnumbered for a reason. I want to show how it migrates. Okay, see that unnumbered one over here? So let's leave that unnumbered. Now this right here is just a single bond. Okay, so I want to make that clear. It's just to show the relative geometry there. All right, so let's see how this works. All right, so let's redraw this. Sorry, I made it a little small. All right. So what happens first is we're going to grab a hydrogen. All right, so this is a mechanism that we'll see later on. Okay, so 2, 3, 4, 1, 5. So here's a carbocation. Here's 6. This is still a carbon atom, so let me just circle that. Okay, and then there's a hydrogen right here. All right, plus Cl minus. All right, so let's renumber these one as well, so we get an idea here. Okay. So what happens here is you're going to have an alkyl migration. So let's draw that. Alkyl migration. All right, so this bond right here is going to move right there. Okay, so it looks like a bond's going to break. All right, so then here, let's keep track of what we just drew here. Boom, boom. So what happens there is that if I kind of think about the bonds here, now I have 1, 2, 3, 4, 5. So now I'm making a 5-membered ring. And this is what that is right down here. Okay, so now I made a 5-membered ring. Here's the plus charge. So usually this contraction happens because the ring size is too small. So on the left side here, we actually have a 1, 2, 3, 1, 2, 3, 4. So this side right here, this is a 4-membered ring. Okay, 1, 2, 3, 4, 5, 6, and this is a 6-membered ring. All right. Well, what do we know about 4-membered rings? Are they particularly stable? Nuh-uh. So we're going to sacrifice a 6-membered ring to get 2 5-membered rings. So that's a lot more stable. So chlorine here will then now attack this position. Okay, so now this is 1. 4 has moved all the way over here. 3, 2, and then 6. All right, because now the 4th carbon, see this 4th carbon right here? It no longer has a bond right here. It no longer has this bond. So that bond has been broken. That's why there's a positive charge there. Okay, good. All right. And that's the product. All right, so you can get, so this is what we call ring expansion / contraction. One ring got bigger, one ring got smaller, and that usually how it happens in acid for alcohols. Or alkenes, actually this is for alkene. So whenever acid's involved. All right, well I know we don't have much time left. We'll spend a little more, just a few more minutes over here. One last example, and that's it for carbocation. So this is called pinnacle rearrangement. So I don't think this has any relationship to pina coladas, but I'm convinced maybe it does, because if you look at pinacolone, they have some sweet aromas, but I'm not sure. I didn't do much research into that. But pinnacle rearrangement, okay, is a very classic example where this will rearrange in a peculiar way. So, pinnacle is this this diol. We call this a vicinal diol. All right, and somehow it gives you this, pina colon. All right, so this is pina colon. 70% yield. All right, let's go over how this works. So you get 2 OH groups. Then you have sulfuric acid, HOS, OH. So let's draw one atom here. This will give us the pina colon intermediate. All right, so, well, this will form a very stable carbocation, so let's go this way. But then we get a situation where this positive charge, what do we do with it? The sulfuric acid won't attack it. It's too unreactive as a nucleophile. So the next best thing is a methyl migration. All right, so we haven't seen this type of mechanism before, but we'll see this a lot. Okay, boom, and the methyl here travels and goes to the carbocation. So we have a methyl shift. And then the base here, HSO4 minus. Anything that's partially has lone pairs can act as a base. And then bam, you get to the final product, pina colon. So that's another mechanism, and we'll see this mechanism a lot, especially in the labs we'll do in 18B. All right, that's it for today. See you guys in lab.
Wait, can you leave that over? Please?
Yep. Probably not. Hey, what's up?
I have a question.
Yeah.
So I took science today, and I really only thought we were being quizzed on the NMR stuff, so I didn't know if we were being quizzed on the SC1, SC2.
Okay, how about you just take the IR quiz today? Did you review IR?
Yeah.
Okay, why don't you just take that one today? We could take the next one in office hours or something. Yeah.